Welcome viewers. Today in this part of the course we are going to talk about signal distortions and noise which is encountered when a signal passes through a channel. So, to start with, we will build on the concepts we learned in the previous lecture about LTI system and the signal propagation through an LTI system. So, today we will define what is we call a channel transfer function, and then we will talk about signal distortions, which are distortions in terms of amplitude and the phase response, and we will introduce the notion of signal bandwidth and define what is baseband signal and passband signal, and lastly we will talk about noise. So, what we saw earlier is that when a complex sinusoid signal passes through an LTI system, the output is given by a complex scalar times the sinusoid function of the same frequency. Using this concept, now we will define what is the transfer function of an LTI system. So, let us assume that HF is the transfer function of an LTI system, and we are now going to see how the input signal, when it passes through LTI system, the output of that system is related to the transfer function and the input signal. So, now first we make use of the fact that we can always write any finite energy signal as a linear combination of the sinusoids which are defined through the coefficients which are given by Fourier transformation. So, let us say ut is the signal in the time domain and capital UF is the Fourier transformation of the signal. In that case, the transfer function of channel, which is HF, and the Fourier transformation of the signal UF will define the output of the signal, which is going to be Yt is equal to integral minus infinity to infinity capital UF HF e to the power j 2 pi f t df. This is the representation we can get if we remember or recall the convolution formula. Now, if we also recall the formula for inverse Fourier transformation, we can say that UF into HF times e to the power j 2 pi f t is the inverse Fourier transformation of the signal. What it means is that we can then define YF, which is the Fourier transformation of the output signal, as product of input signal Fourier transformation times the transfer function of the LTI system. This relationship between the output signal frequency response and the input signal frequency response and the transfer function of LTI system allows us to very simply describe the response of an LTI system to any given signal. So, this transfer function we are now going to use to describe what kind of distortions can be expected for a system when a signal passes through this LTI system. So, to start with, we will consider a real valued sinusoidal input. Let us say our input is ut. This is the example which we considered in the previous lecture, and we computed the output response for this sinusoidal signal for a transfer function which is given by HF. So, now the output signal Yt is going to be related to the transfer function, which is the magnitude of the transfer function times cos 2 pi f naught t plus theta plus phase phi, which is going to be the angle of the transfer function. Now, what it means is that when a sinusoidal signal passes through an LTI system with the transfer function HF, the output signal is amplitude scaled by the transfer function evaluated at frequency f naught and goes through a phase shift, which is the angle of the transfer function at frequency f naught. Now, let us try to understand when a system is called distorted or signal is called distorted and when it is useful, which is we say distortionless signal. If there is a signal which is passing through a system and if there is only a constant amplitude scaling and there is a time scaling which is a time shift, then in that case we can perfectly recover the signal at the receiver side. It means if there is a signal which is only going through a constant amplitude scaling and a time shift, then we will call this signal is distortionless. So, for a channel to be distortionless, the transfer function or the impulse response of that signal has to be k, which is the constant amplitude scaling, times impulse response at t minus capital T, where capital T is the time shift introduced by the channel. This impulse response can also be represented in the transfer function form as capital K e to the power minus j 2 pi f t naught, where capital K is the constant scaling for frequency components and e to the power j 2 pi f t naught is the component which is defining the phase. It means the phase of this transfer function has to be linear in order to have a distortionless transmission. Now, if there is any signal or system which does not have frequency independent scaling and linear phase response, then that system will cause distortion on the transmitted signal x t. The major type of distortions are amplitude distortion. Amplitude distortion is caused whenever amplitude is not constant in the desired frequency band. Then there is another kind of distortion is phase distortion. If the phase response is not linear in the desired frequency band, it will lead to phase distortion. There are other kinds of distortions also possible. These are non-linear distortions and are primarily caused by non-linear devices which are in the signal path in the communication system. And the examples for these kind of non-linear devices are mixers, which are used for up converting or down converting the frequencies, and power amplifiers, which are used to amplify signal for a transmission over longer distances. Apart from this, if your signal propagation is through free space, there can be distortions caused by multipath. If there are multiple reflected path combining at the receiver, it will also lead to some kind of constructive and destructive interference and will cause distortions. So, here is an example of a rectangular pulse which is passed through an RC low pass filter. The impulse response for the function is shown in the second graph, which is exponentially decaying function, and we can see that the output is distorted. It is no more rectangular pulse, whereas it is some kind of pulse which is increasing exponentially, and then there is exponential decay, whereby we see that the signal is not passed through the channel without distortion, and these kind of distortions can lead to errors at the receiver in the interpretation of the signal what was transmitted. In order to understand in detail about what is the effect of these kind of distortions, first we need to characterize what is the signal occupancy or frequency occupancy of a signal, because we said that for a distortionless transmission, amplitude of the transfer function has to be constant over the frequency band where signal is having non-zero amplitude. Also, for phase distortion, we should have linear phase over the frequency band for which signal is having non-zero amplitude. So, first we will define what is the area or the frequency range which is occupied by signal. For this, we will introduce a concept of energy spectral density. So, what is frequency energy spectral density? The energy spectral density of a signal is that for different frequency component, what is the energy content. So, for computing this, what we are going to do is we are going to look at Fourier transformation, which will allow us to compute the amount of energy which any frequency component of frequency f has. So, once we have this energy spectral density or power spectral density in the case where signals are not finite energy, but they are finite power signals. So, based on certain measures of the desired criteria, we can then introduce notion of bandwidth, which is the range of frequencies which is desirable, and we want our signal over those frequency components to go without any severe distortion from the channel. So, what is energy spectral density? If you consider Fourier transformation of a signal ut, which is denoted by uf, then mod of uf square is called energy spectral density, and if we integrate the energy spectral density over the entire frequency range, the integral will be equal to the energy of the signal. Now, once we have energy spectral density, we can now define the concept of bandwidth. So, loosely speaking, bandwidth of a signal ut is the band of frequencies which are occupied by the Fourier transformation uf. Now, why do we call word loosely? Because this term loose is in a way related to a very fundamental result in communication theory or signal theory, that any signal cannot be both limited in time and limited in frequencies. So, all the practical signals which can be generated are going to be limited in time. So, no signal which you will encounter ever in your life is going to have limited range in frequencies. If it is not contained in certain frequency range, then how are we going to introduce this concept of bandwidth? So, there are several criteria which can be put forward. One of the simplest criteria could be that you define the range of frequencies for which the signal energy goes within certain fraction of the peak signal energy. If we define this fraction to be half, then the corresponding bandwidth is called 3 dB bandwidth. Also, we can define a bandwidth in terms of the frequency, the smallest frequency band which occupies a certain fraction of the signal energy. This fraction could be 90%, 95%, 99%, and based on what fraction we are defining, the bandwidth of the signal would be different. While doing computation, we will only consider for bandwidth, we will only consider positive frequencies, because we know that Fourier transformation, whenever we compute Fourier transformation for any real signal, we will have both positive as well as negative frequency component. But the purpose of bandwidth, we will only consider positive frequency components. So, now here is an example where we are considering a time domain signal which is sync 2t, where time t is in microseconds. In that case, the Fourier transformation of the sync pulse is going to be a rectangular pulse which will be having spectrum between -1 megahertz to 1 megahertz. So, we will have bandwidth of the signal which is 1 megahertz, because negative frequencies will not be counted. Let us take another example. Now, consider a time domain waveform which is limited in time. This is a more practical case, because the previous waveform was sync, which was extending from -infinity in time to +infinity, not realizable, and that is why the frequency response was limited in time, but that was more of theoretical importance. Now, what we are seeing is one of the most commonly encountered communication signal, which is called gate pulse. So, for a gate pulse which is confined to a time which is from 2 microseconds to 4 microseconds, if we look at the Fourier transformation, which will give you the frequency occupancy of the signal, we will get a sync function, and to define bandwidth, we will have to use a concept of frequency range which occupies a certain fraction of the signal energy. For example, here we have considered 99% of the signal energy, and we are going to define bandwidth as the frequency range which contains 99% of the signal energy. And by solving simple equations, we can see that for signal which is occupying a band in time from 2 to 4 microsecond, the signal bandwidth turns out to be approximately 5.1 megahertz. If we suppose want to reduce this fraction of energy, let us say to 95%, the bandwidth would be smaller than 5 megahertz, and if we want higher fraction of the energy like 99.5%, signal bandwidth would be much higher as compared to 5 megahertz. We can define meaningfully bandwidth only if we define what is the fraction of energy we are interested in. Now, how do we decide what is the fraction of energy we are interested in? It depends on a very important concept called signal to noise ratio, which we will introduce little later when we start talking about noise, and there we will also define that how do we define the what fraction of energy we should be interested in. Here we have seen that if the fraction is given, how do we calculate the bandwidth of the signal. Now, since we have defined the bandwidth of the signal, we can also classify signals based on their frequency domain response into two classes. One is called baseband, another is called passband, and these play a very fundamental role in defining or classifying the communication systems. So, a baseband signal is a signal for which the frequency range is centered around 0 hertz or DC component. So, what we say is that a signal is called baseband if its frequency response is 0 almost for all the frequencies which are greater than some bandwidth W, and a passband signal is a signal for which the energy is concentrated away from DC and around a carrier frequency denoted by Fc. So, outside from band around Fc of width W is going to contain most of the energy or the energy which we are interested in. We can always classify signals into either baseband or passband. In the next few slides we will see examples of baseband and passband signals. So, here we will see an example of baseband signal. So, what we see is that frequency spectrum is centered around 0 and there is no frequency component beyond W. The negative frequency components are artifact of mathematical analysis used for Fourier transformation, those are not of interest. We will notice one more important thing, that all the real signals, the magnitude of frequency response or Fourier transformation is symmetric around the y axis and it is conjugate symmetric around, amplitude is symmetric and the phase is conjugate symmetric around the y axis. Now, we see an example of passband signal. We see that the signal energies are now centered around Fc and we can clearly see that the magnitude is symmetric around y axis and phase is conjugate symmetric around the y axis. So, what we have already seen now is that what is the kind of distortion signal can experience when signal passes through an LTI system. Now, we are going to talk about another kind of distortion which is typically additive in nature and is almost present all the time, whether the channel is distortionless or not, noise is always present. So, noise is the term which is generally referred to any undesired signal or disturbance that masks the desired or received communication signal. Now, there can be two type of sources for this noise. Broadly speaking, they are called internal sources or external sources. So, internal sources of noise include different electronic devices which are part of communication system, like active electronic devices such as amplifier and oscillators, or passive circuitry like filters which provide some insertion loss. And for external sources we can have atmospheric, solar and cosmic noise, or we can have some other man-made sources such as intentional or unintentional interference jamming. These external sources are external to the communication system. Now, we will mainly focus on internal noise. So, the first kind of noise which we are interested in is called thermal noise. Thermal noise is the kind of noise generated by all kind of resistances and like resistors, semiconductors, resistance of a resonant circuit and real part of the impedance of any transmission line, cable, and it is mainly due to the Brownian motion or random motion of electrons, and the noise power generated through the thermal noise is given by K, T, B, where K is the Boltzmann constant, T is the absolute temperature of the device and B is the bandwidth of the signal in which we are interested in calculating the noise. So, what we can see from here is that there is no frequency dependent component. So, thermal noise is often referred to as white noise because it has constant or uniform spectral density. Another kind of noise which is of importance is short noise. Short noise was originally used to describe noise due to the random fluctuations in electron emissions from cathodes in vacuum tubes. This is the reason why this name short noise was given, but this short noise is also caused in semiconductors due to liberation of charge carriers, and it also has uniform spectral density. There are a few more types of noises which are there and which are of value, and when we have baseband signal, these all kind of noises will affect. When we have passband signals in higher frequency range, mainly the noise which affect are short noise and thermal noise. So, the other three noise which we are going to discuss in this particular topic are flicker noise. This is caused by active devices, integrated circuits, diodes. This is due to the combination and recombination of the carrier components. Then there is another type of noise which is important. This is called axis resistor noise. So, in some of the devices your thermal noise can be frequency dependent also. So, that extra component which shows the frequency dependency is called axis resistor noise. Then there is something called burst noise or popcorn noise, and this is the noise which is due to the different kind of charge generation phenomena, and it has spectral density which reduces or decays with inverse of the frequency square. So, at higher frequency component this noise power is negligible. Now, we will introduce the concept of signal to noise ratio. As we said that concept of bandwidth is also related to the concept of signal to noise ratio. So, signal to noise ratio is defined as the ratio of signal power to the noise power. So, what are we interested in? We talked about thermal and short noise, that they have uniform spectral density. So, if we are interested in wider and wider signal frequency ranges, then what will happen? The signal energy is finite, whereas the noise energy would keep on increasing. So, signal to noise ratio is defined as the ratio of signal power to the noise power. So, here we will try to now correlate kind of fraction of signal energy we should be considering for defining bandwidth. Now, we have already understood that the signal bandwidth is only for signals which are of finite energy. So, signals have finite energy, and if we want more and more fraction of the signal energy to be considered, we will have to go for wider frequency range, which will lead to linear increase in the noise power. It means that if we go for higher fraction of signal energy, we might end up with lower signal to noise ratio. So, that is why there has to be a trade off in what is the fraction of signal energy we are interested in, based on what is the signal to noise ratio which we are interested in at the receiver side. We cannot keep on going for higher and higher fraction of signal energy, because ultimately that will lead to a poor signal to noise ratio. At the same time, we cannot go for a very small fraction of signal energy, because then the signal might be below the sensitivity level of the receiver. So, there is a trade off when we decide for bandwidth what is the fraction of signal energy we must be interested in, and that depends on signal to noise ratio. So, in order to characterize the noise, which is cumulative effect of the 5 type of noises we have discussed, we can define a factor called noise factor or noise figure. This is actually defined as the ratio of the signal to noise ratio which is at the input of the network to the signal to noise ratio at the output network. Now, this is denoted by f, and if f is equal to 1, then it means that the network is noiseless, and if the network is introducing lot of additional noise, then the value of f will be much higher as compared to 1. For passive elements, the noise figure is equal to the loss caused by the passive element. Typically, this noise figure is defined for temperature which is 290 degree Kelvin, but then your systems can operate at varying temperature ranges, starting from, let us say, for satellite communication, this temperature range can go from -10 degree centigrade to 55 degree centigrade. So, we need to have a characterization for noise which will allow us to translate the noise characterization at 290 degree Kelvin in terms of noise figure to something which is more relevant to the operating temperatures. For that matter, we define something what is called equivalent noise temperature. So, the equivalent noise temperature of any communication device or electronic device is related to its noise figure and the source temperature, with the formula that equivalent noise temperature T is equal to F minus 1 times Ts. So, now though the noise figure was calculated only for 290 degree Kelvin, which translates to roughly 17 degree centigrade, we can also use this formula for different source temperatures. Typically speaking, any communication system is not a single device, it is a cascade of electronic devices like amplifiers, mixers, some more amplifiers. So, how do we characterize the noise figure or noise factor of such a cascade of networks? So, for that we can use, so here we see that there is a cascade of some devices which are offering gains G1 and with the noise factor, let us say F1, and second device having a gain G2, noise factor F2, third device having a gain of G3, noise figure of F3, and so on. So, if we are looking at the input of this device, so what is the equivalent noise figure of this cascade of devices from at the input, that is given by F1 plus F2 minus F1 by G1 plus F3 minus F1 by G1 and G2 and so on. What we get to know from here is that the equivalent noise figure or noise factor of a cascade of systems is mainly contributed by the first device. That is the reason why in most of the communication system, the first device is the low noise amplifier, which has a low noise figure and provides moderate gain. Because if we go for higher gain in the first stage, the noise figure will also be high and the equivalent noise factor for the entire cascade will be much higher, leading to a lower signal to noise ratio at the output of such system. So, what we learn from here is that whenever we are considering any cascade of network, the first element has to be the one which has very low noise figure, even though at the cost of a moderate gain, and this formula is called as Frisch formula, and it allows us to estimate or analyze what is the equivalent signal to noise ratio what we are going to have for a cascade of network. To summarize, today we have looked at the transfer function of LTI system, which allows us to simply describe the relationship between input and output of an LTI system in terms of its frequency response, and also allows us to characterize the properties of LTI systems which allow distortionless transmission, and allows us to understand various kind of distortions which can be introduced by non-ideal amplitude and phase response of an LTI system. We also use the concept of energy spectral density to define what is the signal bandwidth, which is loosely speaking the frequency range which contains the fraction of signal energy, which allowed us to further classify signals into baseband and passband signals, which going forward are going to be the one of the most important classification when we discuss in this course further about modulation techniques. In the end, we also talked about noise which is added into the signal when the signal passes through various communication systems and communication channels, and all this will be useful when we start looking at practical techniques using modulation and allow us to characterize the output performance of different modulation techniques.